would like to find the electric field at a point at a distance of r from the center of a long wire with a linear charge density of lambda. The linear charge density is basically a measure of the charge per unit length. So the linear charge density, which is denoted by lambda, is essentially equal to Q by L. Now, in order to calculate this electric field at the distance of r, we're going to use the concept of electric flux. So now we know that electric flux is equal to, electric flux, yes, that's denoted by phi. So phi is equal to E dot S. Even though they are vectors, we're just going to omit that for now. So they're just ES, or phi could also be equal to the charge enclosed by the object divided by epsilon naught. So these two are the same thing. So what we can draw from this is that ES is equal to Q by epsilon naught, but we'll come to that later. Now let us imagine a hypothetical body surrounding this wire. Let's think of a cylinder of the same radius, by the way. It has to be equal to R. Something like this. Be good. And it has to be a cylinder, so in 3 dimensions. Let's have it go downwards. So now let's say that the length of, or rather the height of this sphere is L, right? And the radius is, of course, just R. Let me mark that up here as well. So now let's use the first definition of flux and do something with it. So now we want to find the value of E, which is the electric field. So we're just going to let that be the way it is. We're not going to put in a value for that because we don't know what it is. So phi is going to be equal to the electric field multiplied by S, which is this, which is the surface area. So now let's look at this, this surface which we have constructed around the wire, which does not exist. It's an imaginary structure. We call these surfaces Gaussian surfaces, which we use to calculate flux. So now this wire will emanate electric fields tangential to itself, by which I mean perpendicular to its surface. It won't shoot any electric fields up like that. So we just consider the curved surface area of the cylinder. We do not consider the top surface or the bottom surface. We just consider this curved surface area over here. And now from geometry you would know that that particular surface area is equal to 2 pi RH. So phi is equal to E times 2 pi RH. This is going to be our first equation. Which we derive from this first equation over here. Now let's use the second equation, phi equals Q by epsilon naught, and do something with that as well. So the value of Q here is going to be equal to lambda times L. Since we defined lambda is q by L, we can multiply L on both sides. So we get q is equal to L times lambda. So this is going to be lambda times L divided by epsilon naught. So since both of them are flux, we can equate the two of them and say that E into 2 pi r h actually this shouldn't be an h, it should be an L, because that's what we've taken as the height of the triangle. Not the triangle, sorry, the cylinder. So instead of an h, I'll just place down an L, because that is the height of the cylinder here. So flux will be E times 2 pi r L, as I've written down here, and we use the second equation and equate both of these. The L's cancel out, which shows that the electric field at the point R does not depend on the height of this hypothetical Gaussian surface. The only variables here are lambda, assuming that lambda might change, and r, which is the radius, which is the distance from the center of the wire. So now we have E into 2 pi r is equal to lambda by epsilon naught. And if we just solve this equation, we have E is equal to lambda by 2 pi r into epsilon naught. This is the formula for the electric field due to a charged wire at a distance of r with a uniform charge density of lambda. Thank you.